Hello everyone! Welcome to another awesome episode of Pisikaalalman. This is Ma'am Allen, and for today we will discuss about electric forces and electric fields. To be specific, at the end of today's episode, you will be able to calculate the net electric force on a point charge exerted by a system of point charge. Number 2, describe an electric field as a region in which an electric charges experience a force. And lastly, calculate the electric field due to a system of point charges using Coulomb's law and the superposition principle. But before we begin, let us have a short recap of what we have discussed last episode. Atom consists of electrically charged particles such as neutron, which is neutrally charged, proton, which is positively charged, and electron, which is negatively charged. The quantity of charge can be defined in terms of the number of electrons. The unit of charge is in coulomb and has a symbol capital letter C. 1 coulomb of charge is equal to 6.25 times 10 raised to 18 electrons. Imagine how many electrons were there in 1 coulomb. Which means the charge of a single electron is equal to negative 1.6 times 10 raised to negative 19 coulomb. We also observed and experienced how charges transfer from one object to another. As you can see on the screen, the processes on how we can charge an object and transfer it from one body to another is by rubbing, by conduction, and by induction. We also deal with the interaction between two electrically charged objects and the law of electric charge. We say that unlike charges attract and like charges repel. Pairs of electrical charges interacts with each other according to the law of electric charge. What do you call to that force around electrically charged object and is also responsible for the interaction between two or more electrically charged particles? Do you know what force is that? We call that as electric force. The attractive or repulsive interaction between any two charged objects is an electric force. We use the symbol capital letter F subscript E to represent electric force. Unlike gravitational force, which is attractive in nature, electrostatic force can be attractive or repulsive. Try to explore the simulation by opening the link provided. Each group are given 5 minutes, and after that, you may share your observations and experiences to your classmates or even to your household members. To guide you with the simulation, here's the guide question for each group. I hope you enjoyed the activity. After the simulation, we were able to determine the factors affecting the strength of electrostatic force. We say that the amount of charges and the distance that separates them greatly affects the strength of electric force. The strength of an electric force between two charges is given by Coulomb's law. It states that the electric force between two charges is proportional to the product of the charges and inversely proportional to the square of the distance between them. The magnitude of the force of attraction or repulsion between 2 point charges is directly proportional to the product of the two charges and inversely proportional to the square of the distance between them. shorter distance between charges will experience greater electric force. The farther the distance gives weaker electric force. Given the relationship between electric force, the value of the charge and the distance between them, we can rewrite the relationship into equation form, wherein electric force is equal to electrostatic constant K multiplied by the product of Q1 and Q2 divided by R squared, wherein Q1 and Q2 are the amount of charge and R is the distance between them. The electrostatic constant K is equal to 8.99 times 10 raised to 9 Newton meter squared per Coulomb squared. You can also get the exact value of K by solving this equation. K is actually equal to 1 over 4 pi epsilon sub 0, or the permittivity of free space. If you calculate this equation, it will give you the value of K, or the electrostatic constant. Epsilon sub 0, or the permittivity of free space, is equal to 8.25 times 10 raised to negative 12 Coulomb squared all over Newton meter squared. If the unit of K is in Newton meter squared per Coulomb squared, while the charges is in Coulomb and the distance is in meter squared, we can cancel meter squared and we can also cancel Coulomb squared. Therefore, the unit of electric force is in Newton. Let's have an example. The electron and proton of a hydrogen atom are separated by a distance of approximately 5.3 times 10 raised to 11 meter. Find the magnitude of the electric force. Given the charges of electrons and protons, which is equal to 1.6 times 10 raised to negative 19 coulomb, and R, which is equal to 5.3 times 10 raised to negative 11 meter. Also given the constant value K, which is 8.99 times 10 raised to 9 Newton meter squared per Coulomb squared, we use the equation electric force is equal to K Q sub 1 Q sub 2 over R squared. We substitute the value of charges. Also, we substitute the value for the distance. We cancel the unit meter squared and Coulomb squared. Then we get the answer 8.2 times 10 raised to negative 8 Newton. If there are multiple point charges, the forces can be added by using the superposition law. That's how we calculate electric force using Coulomb's law. Do you have any question? So let's proceed. all charged particle will experience a force around it. And that region around an electrically charged particle where force is detected is called electric field. The symbol for electric field is capital letter E. The strength of the electric field is defined to be the force per unit charge experienced by any point charge. Since the field strength is a force divided by a charge, the units are in Newton per coulomb. Or we use capital letter N over capital letter C. Mathematically, this can be expressed as electric field is equal to electric force over charge. Combining the equation of electric field strength and Coulomb's law, we get our equation for electric field around a charge is equal to K multiplied by charge over R squared. A convenient aid for visualizing electric field patterns is to draw electric field lines. They consist of lines drawn tangent to the electric field vector at any point. The number of lines drawn being proportional to the magnitude of the field strength. Therefore, we can say that electric field lines are imaginary lines drawn in such a way that their direction at any point is the same as the direction of the field at that point. Field lines go away from positive and it moves towards negative charges as shown in the illustration. We can also say that the electric field of a positively charged particle is away, while the electric field of a negatively charged particle is towards the charge. Remember the following rules in drawing electric field lines. First, field lines must begin on positive charges or at infinity and must terminate on negative charges or at infinity. Second, the number of lines drawn leaving a positive charge or approaching a negative charge is proportional to the magnitude of the charge. And lastly, no two field lines from the same field can cross each other. Here are examples of electric field lines between two equal but opposite charges and two equal of the same charges. Notice that the line leaves positively charged particle and enters negatively charged particles. Also, electric field is strongest where field lines are most dense. Let's have an example on how to calculate electric field. A charge of 1.5 coulomb present in an electric field produces a force of 0.06 Newton. What is the intensity of the electric field? Given the charge which is equal to 1.5 coulomb and the force which is 0.06 Newton, what is the electric field? Using the equation, electric field is equal to electric force over charge. We substitute the value of charge and the force. Then we get the answer, electric field is equal to 0.04 Newton per Coulomb. Just as electric forces can be superimposed, electric fields can as well. And to be able to calculate the electric field of multiple point charges, we get the resultant of electric field. The net electric field is equal to the sum of the individual electric field. The magnitude of electric field on each vector is equal to K multiplied by Q over R squared. That ends our lesson today. I hope you learned a lot in our today's episode. See you again next time and have a great day.